Now, let's discuss zero carbon design. Similar to the zero energy design, this framework also emphasizes reduce in both embodied and operational carbon and regenerate through nature-based solutions to offset the resulting carbon emissions from the built environment. Let's look at zero carbon design strategy. Similar to zero energy design, the zero carbon framework has two key principles: reduce and regenerate. On the reduce side, we need to minimize embodied and operational carbons as much as possible through bioclimatic design. We also need to choose low-impact materials as well as energy-efficient building service systems and renewable energy integration. The other side, regenerate, uses nature-based carbon uptake for carbon emissions from material production, construction activities, and building operations. Nature-based solutions are at the building and the site levels. This slide presents interconnected elements of zero carbon design strategies. Similar to zero energy design, the zero carbon approach consists of bioclimatic design, energy efficient building systems integration, and renewable energy systems. In addition, the zero carbon buildings use low impact building materials, and all the embodied and operational carbon are offset by real time nature based carbon sink. This slide explains another reason why we need to push further to implement carbon neutral buildings. We looked at IEA's roadmap to meet carbon neutrality in the building, manufacturing, transportation, and energy sectors. In that roadmap, by 2030, all new buildings must be zero carbon ready, and more than 85% of both the new and existing buildings must achieve zero carbon status. This chart projects US building floor area. By 2050, an additional 170 billion square feet of construction will be added to 320 billion square feet of existing building stock built prior to year 2022. The data reminds us that even though new construction happens at a fast pace, the vast majority of buildings in 2050 will be adapted from existing building stock. Designing and retrofitting these buildings with zero carbon principles is an essential opportunity to significantly reduce emissions. Bioclimatic design is one of the fundamental and highly effective design strategies for reducing operational carbon emissions from the early stages of building design. It involves taking advantages of the climate conditions around the site, using proper building orientation, and strategically placing windows for optimum daylight and natural ventilation. Natural ventilation reduces mechanical load while supplying clean air for users. Daylighting reduces artificial lighting demand while providing connections to outdoor views. Passive heating utilizes sunlight during colder months and reduces heating load. Bioclimatic design connects these principles to the reduce framework. Again, bioclimatic design is essential to achieving zero carbon buildings. This building section drawing highlights key environmental factors that are important in tropical regions. 1. Humidity levels are important for regulating thermal comfort and reducing the load on mechanical systems. High moisture levels cause thermal discomfort, and dehumidification to remove moisture from the air requires high energy. 2. Temperature affects passive design strategies like shading and material choice, which help create a cooler indoor climate. 3. Radiation assists in decision-making for optimal building orientation and facade design, such as apertures and shading devices, which help control solar heat gain. 4. Air movement promotes natural ventilation and minimizes energy-intensive cooling and ventilation. Using low-carbon materials is important for carbon-neutral buildings. Every building material carries embodied carbon resulting from the environmental impacts associated with material fabrication, transportation, and construction activities. Choosing low-carbon materials connects to the REDUCE framework. The chart on the right compares the embodied carbon and embodied energy of structural materials for a unit weight kilogram. Glulam materials have negative carbon emissions, minus 0.76 kg carbon dioxide per kilogram, as they act as a carbon sinks during their life cycle. Steel, on the other hand, emit 2.7 kg CO2 per kilogram. Concrete materials are moderately impactful with 0.15 kg CO2 per kilogram of its unit weight. Now, let's look at embodied energy, megajoule per unit weight kilogram. Embodied energy refers to the total energy consumed during manufacturing, transportation, and assembly. Glulam materials have an embodied energy of 8.9 megajoule per kilogram due to the manufacturing process involved in producing engineered wood. Steel has 42 megajoule per kilogram of embodied energy due to an energy-intensive manufacturing process, making far more carbon-intensive. Using steel with a high recycling content can reduce its carbon footprint. Concrete materials are around 1.09 megajoule per kilogram. Just as selecting structural materials with low embodied carbon is essential, choosing low-impact materials for facade systems is equally important. This chart compares the embodied carbon and embodied energy of materials such as bamboo, rammed earth, brick, and aluminum. Renewable materials such as bamboo and rammed earth have significantly lower environmental impact compared to aluminum. Having a high recycled content is essential to reduce the carbon footprint for aluminum. The next two slides show reference data sources from the IPCC 6th Assessment Report. IPCC stands for Intergovernmental Panel on Climate Change. Again, selecting materials with low embodied carbon and energy is a climate action strategy that is critical for achieving carbon neutral construction. Understanding these life cycle impacts can guide us toward more sustainable design choices. This slide highlights various material innovations that significantly reduce embodied carbon. For example, bamboo and CLT cross-laminated timber boards are renewable, low-carbon alternatives to traditional flooring and structural materials. Mycelium and bioconcrete materials are breakthrough materials that not only reduce carbon but also regenerate building materials. Recycled materials such as recycled rubber roofing and denim insulation are creative examples of turning waste into functional building materials. The use of low-impact materials aligns with the REDUCE framework. Next, let's explore renewable energy integration, a critical element in achieving zero-carbon buildings. When we looked at zero-energy approaches, renewable energy systems connect to the regenerate framework to offset the energy use. However, for zero carbon, it aligns with the REDUCE framework because renewable energy offsets operational carbon compared to, let's say, a building powered by a coal power plant. This slide showcases diverse applications of renewable energy across infrastructure, urban spaces, and buildings. At the infrastructure level, solar panels not only generate clean energy for community or city use, but also provide environmental benefits like reducing canal water evaporation and producing fresh water from saline water. Similarly, in urban spaces, solar panels power nighttime lighting and charging stations on urban benches and shelters. At the building level, solar systems enable buildings to operate off-grid, providing energy independence and enhancing resiliency during climate emergencies. They can be integrated with facades as seen in projects like Blue House, the Novartis Pavilion, and the FKI Tower, or applied to rooftops such as Apple headquarters. This solar facade design are a balance between solar performance and architectural aesthetics, demonstrating how renewable energy systems can play a role in innovative architectural design. Finally, buildings contribute to both embodied and operational carbon emissions, making real-time carbon sequestration essential for achieving zero or even carbon negative buildings. This slide features iconic examples of integrating nature into buildings. Park Royal Pickering in Singapore is a hotel that incorporates lush greenery on the balcony of hotel rooms, providing biophilic experience for users and enhancing carbon capture. Vertical Forest in Milan is a high-rise covered with trees and shrubs that act as a living carbon sink. Le Nouvel Tower in Kuala Lumpur integrates vertical gardens along the facades for various flora for carbon sequestration. Nature integration can be done at the building, site, and community levels. Their benefits are not only carbon sink, but also additional environmental and social benefits, mitigating heat island effects, supporting urban ecology, and providing natural habitats. The California Academy of Science building in this slide illustrates how green roofs contribute to high-performance building carbon capture and aesthetic value, and seamlessly blending with the landscapes and urban surroundings. The Perez Art Museum in Miami serves as another excellent example of nature integration. The expansive roof canopy creates an interstitial space that features hanging gardens resembling green facades. These gardens contribute to a more comfortable urban microclimate, enhance the vibrancy of public spaces, and function as carbon sinks while improving air quality. This slide shows Southwest Montgomery Green Street in Oregon, where trees, landscapes, and other green infrastructure mitigate rainwater runoff, support biodiversity, create inviting public space, and contribute to carbon sequestration and pollutant filtration. Different ecosystems offer different carbon storage capacity. Wetlands are among the most efficient, storing up to 643 tons of carbon per hectare. Incorporating constructed wetlands into site designs significantly contribute to carbon sequestration while creating functional and beautiful landscapes. Forest and grasslands also play an essential role, and their integration into urban settings can amplify carbon capture, urban ecology, and healthier built environment. Another innovative nature-based carbon sink integrates microalgae living components into building systems. This slide shows a microalgae window system installed at UNC Charlotte. This system not only reduces carbon from room air, but also improves indoor air quality and regulates solar penetration, enhancing both environmental and occupant health. Similar to the previous comparison, this graph compares the carbon sequestration capacity of different individual plant types, measured in kilograms of CO2 per square foot annually. Vineyards have smallest biomass and sequester approximately 0.4 kg of CO2 per square foot per year, the lowest in this study. By comparison, microalgae are the most effective, capturing up to 4.5 kg CO2 per square foot per year. One reason microalgae has the highest rate compared to other plants is its rapid growth rate and higher photosynthetic efficiency, allowing it to absorb and convert more carbon dioxide in a shorter period. Finally, let's compare the design approaches for zero energy versus zero carbon goals. Both use reduce and regenerate framework. While zero energy focuses on balancing operational energy use and renewable productions, the zero carbon goal is more difficult to achieve. It needs additional strategies such as selecting materials with low embodied carbon and incorporating nature-based carbon sink, such as green roof, green facades, and constructed wetlands. These strategies collectively create a holistic approach to reducing carbon and regenerating a healthy and resourceful built environment.